All right, line P1, learning task number 13. We're going to take a look at problems that are going to involve our autotransformer calculations. So doing a bunch of solves for these. Once again, at the very beginning, we have to lay out the fact that these are transformers, which means that they are going to go and follow all of our transformer formulas. The voltage over the primary, Vp over top of Vs, is going to be equal to the number of turns on the primary over top of the number of turns on the secondary, which is going to be equal to the current on the secondary over top of the current on the primary, right? The current one is the flipped one, the other ones stay the same. We also have got that super important one, VA in is equal to VA out. Once again, power doesn't lie. It's sometimes easier to figure out what we have at the load, figure out what we have at the source, and then work back in from either side before we try to analyze any of our currents. That way we know where we should be ending up with, and if what we have coming into the transformer doesn't line up with what we have going out of the transformer, we know that there's an error inherently, and we just got to go back through and sort where that's going to be. Let's start with the very first one that they have over here. They're asking us about a transformer, an autotransformer, that has got a grand total of 600 turns over here in the total winding, and then I've got the secondary that's going to be connected across 520 of these. And they're telling me that they've applied 240 volts to the primary over here. What we're going to do is we are just going to go and establish the volts per turn. It's going to be a little bit different process than what they're going through inside of theirs, but it just makes a bit more sense to be able to go and do so. Volts per turn is simply going to be the number of volts that I have on a given side over top of the number of turns that I'm going to have on that other side, and then it's going to give us a decimal number. It could be a whole number, it could be a partial number, but then we're able to go and just translate that into the opposite side. So let's do that off of this one. We see we have got 240 volts over top of 600 turns over here. This is going to be my volts per turn. We'll plug that in there. 240 divided by 600 equals a value of 0.4. In other words, for every single one of those turns, I'm going to go and have 0.4 of a volt that is going to be across that. Well, if this side over here is made up of 520 turns, these are the same shared turns over here. So I can just go and take that 0.4 volts that I have per turn and multiply it by the number of turns that I have over here. I'm going to do that, my volts per turn that I have over here, I'm going to go and multiply that times 520. And when I do that, so 0.4 times 520 equals a value of 208 volts. So my secondary over here is going to be 208 volts that we will have off of it. Perfect. That gets us to our total amount of volts on the output. We've got our total amount of volts on the input. The rest of this now, what we want to do is we want to figure out our currents that we're going to have. Because once we get these currents, we can then figure out, the VAs and everything else. So we're going to go and take this 208 volts. I see it's over top of a certain amount of ohms over here, which means that I can go and convert that into an amperage. Alternatively, what I could also do is I could convert this directly into a VA. And I'm going to do the VA first, and then I'm going to just drop the VA onto both sides, and we'll make sure we do the matchy-matchy thing after that. So if I take this 208 volts and this 10 ohms, I know that power is equal to my E squared. Can't draw number 2 here apparently today. I have practiced E squared over top of R. So I'm going to go and take 208 squared divided by 10 ohms. That's going to tell me the total amount of power. 208 squared divided by 10 gets me to a value of 4,326.4 VA. 326.4 VA. Well, if that's my VA that I have on the output, it's all coming from this side over here. So I should be able to go and insert the same VA right over there as well. 4326.4 VA. And what I can then do is on both sides, I can take my VA and I can go and divide my VA by the volts to go and figure out what I've got for my amps that I'm going to have inside of there. We're going to do that. We're just going to go and take our VA, divide out the volts, giving us the amps that we are going to have out of there. So we'll take this 4326, we'll divide it by 208. So 4326.4 divided by 208 gets me to a value of 20.8 amps. So this side here is going to have 20.8 amps. And then I'm going to do the same thing on the other side. Let's clear this. 326.4 divided by my high side voltage over here, which is 240 volts, equals 18.03, roughly. 18.03 amps that I'm going to have over here. Lovely. Well, what do we know about current? We know that all of our current that goes into something has to be the same amount of current that's going to be coming back out of it. So if I were to assign instantaneous polarities to anything, I don't really care which one we want to go and assign the instantaneous polarities to, but we can go and say that this is going to be our negative. This over here will be our positive. It's AC, so it's not actually negative and positive all the time. We're just freezing time. What I would see is I would have 18.03 amps that would be coming in, 18.03 amps that would be entering that junction. Actually, I'll put that on the other side over here. Then what I would see, if this is the positive over here, this is still a load that we have attached to this one, which means that I'm going to have that same 18 amps that's going to be leaving from here. So that 18 amps, we must have had some of that current that's going to go and divert down and through this, right? We're going to have to be leaving over there, which means that this is going to be the positive, which means that's a positive over there. And in relationship to that positive, this point here is a little bit more negative. So over here, I've got 20.8 amps. So I have got right over here 20.8 amps that is heading down that, which means that I must have some differing amount of current that is coming in right over here. It's going to have to go and come in from there to go and add on to this, right? So we're going to just go and take that 20.8, and then we are just going to go and minus, just going to divide by, that 18.03, which gets us to 2.77 amps roughly. We have a little bit of rounding that's going to be inside of here. So I've got 2.77 amps inside of there. If I take a look at 2.77 amps, that 18.03 add up to become that 20.8. That 20.8 goes through here. When it gets back to here, it's going to split. 2.77 goes back up into there. The remaining 18.03 is going to be exiting our circuit over here. We have satisfied Kirchhoff's law of current. The last thing that we're going to do, just to get into the practice of it, is to take a look at which of these two transformer windings are going to be the source winding and which of them is going to be the load winding. Remember that every transformer has an electrical load winding and an electrical source winding. So if I take a look at this one over here, I see that there's a positive over here and a negative over here, and the current is flowing from positive to negative. That to me tells me that that must be the source winding. This one over here, I see that I have got current that is entering in over here. It is a negative. This point in relationship to that is going to have to be a bit more positive. It's going from negative to positive, therefore that is going to be my load winding. When you are doing current analysis on transformers, it can be really, really confusing unless you hold that idea out there that you must always have one side that's going to be your source winding, one side that's going to go and be your load winding on them. KCL works out on this one. All right. Good enough. We've got that thing done there. Well, actually, hold on a second here. 2.77 amps that I have inside of here. The actual rating of this transformer itself would be a little bit smaller. It is an autotransformer connection. In reality, this could be a separate winding that they've connected in. If you wanted to find the autotransformer size of this one over here, what you would need to do is you would need to take the volts across a single winding. So in this case, this one over here, that's 208 volts. It goes across from here to here. And we see that we have the same 208 across from there to there. So if we have got that 208 with 2.77 amps, we could go and say that, sorry, I guess I could have kept that in there, 2.77 times 208 tells me that the actual VA of the windings themselves is going to be 576 VA. All right, so that was our very first one that we had. Let's go take a look at our next example. The next example is we are going to go and use this thing as a step-up autotransformer. Now they're telling us that we are feeding this thing in from a 208 volt source. We've got that over top of the 520 turns over here, and that we are feeding that out now to a 10 ohm 240 volt load that we are going to have over here. We don't need to do the volts per turn calculation once again because we already have that. It's the same transformer as what we had before. But if you did need to find the volts, you would take the 208 over top of the 520, so the applied voltage over top of the applied number of windings. That'll tell you the volts per turn, and then you just multiply that by the number of turns. So you take that volts per turn, multiply by 600. That's what would bring you to that value of 240 we're seeing across there. Once you get to that point, you're then going to be able to do the VAN is equal to your VA out. So we can go and take this 240 volts. We're going to go and do, once again, the E squared over R type of formula. I'm preferring doing this one because if we do that calculation where we go from volts to amps using our ohms, and then we use the volts and the amps, we're working off of a calculated value. And if we screwed it up in there, then we're working off of, our own screwed up value. So we're just going to stay away from that. We'll just go straight over to our power. We'll do 240 squared divided by 10 ohms, which is going to go and get me to 5760 VA. That means that there's 5760 VA on this side. There's also going to be 5760 VA on this side over here, which is lovely. Now we got VA in is equal to VA out. Once we have our VAs, we can do that same thing where we figure out our values of current. So we'll take the 5760, we'll divide it by 240, which gets me to a value of 24 amps. 24 amps that I'm going to have over there, and then we'll take that same 5760 and we will divide that by 208, right? Because VA in is equal to VA out. And I see that coming into the transformer, I need to have 27.7 amps. And then coming out of the transformer, I've got 24. So this over here is going to be 27.7 amperes over here. Last thing that we would have to do if we were trying to go and sort out our currents would be, once again, just establish the amount of current that we have going through each one of these windings. One of them is going to be the source, one of them is going to be the load. Let's start by going and freezing some time after we set a polarity. We will make this side the negative, we will make this side the positive over here, but the analysis would work with either one. If this side is the negative, that means that this side over here is also going to go and be the negative. So we can start by establishing directions of current based on those two facts. We know that we are going to have current that is going to be entering into the transformer and traveling up and through, right? It has to go through a load from negative to the more positive end of the load. So I must have 24 amps that is entering in here, driving through there, and then coming back down over here. That's going to be 24 amps over there. This is going to be 24 amps over here. I know that entering into this transformer on the negative, right? You got to remember that my source doesn't see the transformer. Everything that's inside of that is hidden from view. It just sees two lines of 5760 VA that it has to go and supply. So it's going to go and drive current into that. So it's going to drive current in the same direction over here, 27.7. So now I've got 27.7 amps that is driving in here. I see that it hits this little junction over here, and once it hits that junction, some of it comes out over here, 24. The rest of it is obviously going to have to go out over here. You can do the 27.7 minus 24. Spits out a value of 3.7. So I'm going to go and have 3.7 amps that is going to travel up and through here. That 3.7 amps enters into that node with this 24 and comes back out as 27.7 over there. Perfect. What is my actual VA of the transformer that I would need in order to get this 5760 VA type of connection? All I need to do is I need to take a look at a single winding and look at only the voltage over top of that winding. So I'm always looking for the standalone winding, not the one that's made up of two. That's going to be this one over here. 5760 VA over here. And then it is going to go and have 3.7 amps through it. So I can just go and take the 208 volts multiplied by 3.7. Gets me to a value of 769 VA. What I would need is I would need to have a transformer that is built with wire sizing, standalone. If it was a isolation transformer, it would have to be something that's a 769 or a 770 VA type of transformer. We're not going to usually have to calculate that, by the way. This is just practice because we just did this in the previous one. Same with the current analysis. We just did this in the previous one, and it helps us to go through and sort what's happening inside of our transformer. The last thing that I want to point out on this practice over here was that I had current that was going to be driving upwards through there. I had current that was going to be driving downwards through there. And if I took a look at my polarity, this was negative, this was positive, and if this over here is negative, that would mean this is negative, that would mean this is negative, right? It's negative all the way across, which would mean this would have to be a positive up here. So if I take a look at this winding over here, I see that current is going from a more positive section to a more negative section. Therefore, this top one over here would have to be my sourcing winding. This one over here, I see my current is going from my negative up to a more positive place over here. Therefore, this one would have to be my load type of winding. All right, let's go into example number 3. Example number 3 is going to be super complicated. If you take a look through your book, they show example number 3, and then we're going to do this, 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 and we're going to kind of drive through all of these different things. We're going to step through it in a slightly different manner than what they are going to do, because the way that they're doing it, by starting with some of these currents and things like that right off the bat, makes it a little bit harder for us to go and figure out what we have inside of each one of these. The first thing that we are going to do is we are going to go and start by establishing our values that we have of actual voltage off of these ones. It says that this thing is a 120-240 Autotransformer. This would make sense, right? We know that this is going to be my neutral. We know that this is going to be my line. We know it's the neutral. It's the one that's connected, first of all, to the center point where a neutral has to be, but also they show us that this thing has been identified as also being grounded. Back at the source, not at this transformer, but back at the actual source itself. If we take a look at our connections we have inside of here, we see that this one goes across this winding, A to B, which is going to be 120 volts, and then it goes across B to C as well, which is also 120 volts. Therefore, it's going to be 240 volts. This one over here goes over top of 120 volts. This one over here goes over top of 120 volts. And what I'm going to do with that knowledge is I'm just going to go and spit it all out into power. Okay, VAN is equal to VA out. And then we're going to work back from those VAs. Let's start with the first one. The very first one was going to be this winding over here. 12 amps, 240 volts. We can just multiply those together. 12 times 240 gets me to a power of 2880 watts. So I'm going to drop that in, 2880 watts. I'm going to do this one next. It's going to be 120 times 8 should give me 960. 120 times 8 equals 960 watts. And then I'm going to go and do this one, 120 times 10. I'm not going to use a calculator. That's 1200 watts. You should be able to do that one. 1200 watts, 960 watts, and 2880 watts. What do we know about watts? Watts don't lie. What can we do with watts? Can we add them in a series circuit? Can we add them in a parallel circuit? Absolutely. We've got some sections inside of here on this 3-wire Edison that are definitely series parallel. We're just going to add it all together, and we're going to get a total amount of watts. So we are going to go and take that 960 that's there, plus 2880, plus, whoa, that's way too many. 960 plus 2880 plus 1200. Sometimes when I'm tapping with the pen on the tablet, it picks up one too many digits. It's super annoying because I'm looking at where I'm tapping, not necessarily at the display up top. All right, we get, in this case, a grand total of 5,040 total watts that we are going to go and have out. So we're going to drop that in over here. How many volts are we feeding in on this thing? Well, we're feeding in 120 volts, right? Our source cannot see what's inside of here. It's all black box to it. It has absolutely no idea what is inside of this thing. It just knows that we've got 120 volts and we've got 40 watts. Therefore, we must have a certain amount of current that's going to go and supply that. We can go and figure that out. Take that total VA. That's going to be our VAN to feed all those loads. and divide it by 120. When we do that, we end up at a value of 42 amps. So there's going to be 42 amps that is going to go and head into here. And then we're going to go and take that 42 amps and we're just going to start splitting it apart and dropping it down these individual runs that we are going to have over here. We'll establish some values of polarity. It is a AC system, which means that sometimes we are going to be dipping below the neutral plane. Other times we're going to be going above the neutral plane. When we're dipping below, that would mean that my line would be a slight bit more negative than where my neutral would be, right? It's AC, it alternates back and forth. So we'll go with the polarities that are shown inside of the book, because when we do that, it allows us to, follow along with what's inside of the book. Okay, let's go and drop polarity onto everything that we do know about. The things that we do know about is that this is going to have to be more negative, therefore this is going to have to be more negative, therefore this is going to have to be more negative. And if I have got negatives over there, are these sources or loads, do they have the option to be a load? They don't have any option. They are going to go and be loads. These ones over here get a little bit tricky because one has to be a source, one has to be a load. We understand that, we know that, we'll assess that after, but these are all loads, which means that all of these, the current is going to have to travel in and down for each one of these. So if I take a look at this node over here, I know that coming out of that node, I must have 12 amps. It's going to erase that one there and those lines over there. We're going to say we got 12 amps coming out over there. I also know that I've got another 8 amps coming out as well, which means that entering into there, if I've got 2 that are exiting, the third line must have been my entering line, and that's going to have to be the sum of those two. 8 plus 12. Now, we're working with resistive incandescent light bulbs. If we were working with inductive loads, we'd have to apply in power factors and things like that. We're not getting that complicated yet. We will get there in our electrical theory before you're through your full apprenticeship. But for now, we're just going to go and add these together as being straight, pure ohmic resistances here that have got straight, pure ohmic currents that are going to be generated from in-phase currents. So 8 plus 12 gets me to a value of 20. Perfect. That 20 came out of this node, entering into this node. Remember, my source doesn't know it's feeding a transformer, it just knows it's feeding a load, and therefore it's going to be sending its current in on the negative and kicking it back out onto the positive over here. I am bringing in this grand total over here of 42 amps. Well, if we've got that 42 entering and 20 leaving, we know that we must have another 22 that would therefore have to be leaving from that node as well. Kirchhoff's law of current. We have to satisfy that. All right, let's go and carry on with our currents over here. We're now going to go and leave this central bar alone just for a couple of minutes, just because we are trying to figure out, some of these other ones, and this is easiest done as a last step. If you go straight to here, it can get a little bit confusing. This is going to go and have a total of 12 amps that's going through that load. It's going to enter back into that node. This one over here, we don't know where the 10 amps is coming from yet, but we do know that we are going to go and get 10 amps into there, which would mean that if I've got 10 amps entering there and another 12 amps entering there, that I would have to have a grand total of 22 over here. 22 amps. That 22 amps is going to flow up through here. It's going to go and enter into this node over here. Now, we know one other thing about this node. We got 22 amps entering, 22 amps entering. That's a grand total of 4 amps that would have to be entering, right? But then we've got leaving this circuit 42. The sum of all currents that enter a node has to be the same as leaving a node. So if I've got 44 entering and 42 leaving, that means that the remaining 2 amps must be flowing along here. And if we go and take a look, that just makes sense, because we would have 2 amps that would enter here, and then 8 amps that would enter there, and then that would leave us with 10 amps that would be coming back down and through here. The last thing that we need to go and analyze on here is which of my windings is a source, which of these windings is a load, and we can do that just through taking a look at our polarities. Over here I've got a negative and a positive. This current is traveling through here from negative to positive, therefore this would have to be my load type of winding. Over here, if this point was negative, this had to be positive, therefore this had to be positive as well, and this point would be a slight bit more negative. In relationship to that positive, this one would have to be the more negative. And I see I've got current going through from positive to negative, therefore this one has to be a source. You'll see as well that the actual transformer itself, this 120 to 120, they're equal values of voltage, therefore they should have equal values of current. If you end up with anything other than an equal value of current on something that is the same value of voltage across each winding, then you must have some sort of a problem inside of your calculations. What is the actual VA of the transformer that we are using to go and deliver this? Well, we know the VA of our load, which was going to be a grand total of 5040 VA. 5040 watts that we have, but we know that each transformer winding is having no more than 120 volts and 22 amps. So if I do that, 120 times 22, that tells me that the actual transformer itself, in this case, needs to only have a VA rating of 2640, yet I'm able to put out 5040. And the big thing with why we get these magically high VAs out of autotransformers is always just because some of that power is being conducted, right? We're not transforming all of that. We are conducting some of it, and that's what allows us to get these magical high values of current and power and VA and things like that. Ultimately, it still has to come from the source, right? The source supplies everything that is going to be inside of here, but we can do that 5040 watts that we're just developing out here with a much smaller transformer itself. All right. Let's go and take a look at this one over here. This one is going to be a multi-tap transformer that you can utilize to go and take multiple different values of voltage off of. So we are going to go and do a volts per turn calculation off of it, where we are going to go and count the number of turns that I'm going to be placing over top of my primary, the side that I'm feeding into it, and then we're just going to go and figure out the number of volts over top of it. So I got 16 turns over here, plus another 16 turns, that's at 32 then, plus we'll add in that 8, that's going to get us to 40, plus another 24, that's going to get us to 64, plus another 16, which is going to get us all the way up to 80 turns. So I'm going to go and create a volts, 120 volts, over top of 80 turns over here. What I can do then is I can go and convert that into a decimal number. So 120 divided by 80 gets me to a value of 1.5. So I have got 1.5 volts per turn. And all that I need to do now is I need to go and take that volts per turn, and I just got to multiply that across the number of turns that I'm going to have in between given spots. From here to here, we have a grand total of 36 turns, right? 20 plus 16. Multiply that by 1.5. 1.5 times 36 gets me to 54. So I've got 54 volts between those two leads. Over here, I've got 16 turns, so I'm going to take 1.5 times 16. Gets me to a value of 24 volts. Over here, I've got 24 turns. 1.5 times 24 is equal to 36 volts. And then over here, we got 8 volts. 8 times 1.5 is equal to 12. And then over here we got 16, and we calculated a 16 turn before. That was also going to be 24 volts. Which means that now what I can do is just by selecting taps, I can get all sorts of different values that I can go and pull out of this transformer. I can go and connect a load. We'll just take a big old resistor over here. And I could connect that resistor across from here to here, let's say. If I did that, I would get the sum of those two voltages, 24 plus 36. So I would see a 60 volt connection over there. Or if I needed to go and bring the voltage up a little bit higher, I just move this tap down here. Now I'm going to be at a 72 volt connection. And then if I want to go and take that voltage a little bit higher, I can go and take that thing, add this one onto there, and now you're going to be 72 plus 24 is 96 volts that we are going to go and have at that point. So you're able to go and just change these taps to get multiple different values of voltage that you're going to have out of them. It's a fantastic little setup over here. Once again, for a lot of our uses, not super applicable for most places. This is really going to be a place that we need to have multiple values of AC voltage for multiple different things at the same time. Generally speaking, research and development and test benching inside of shops, that are going to be doing repairs on electrical equipment. All right, so this one over here is going to be a variable autotransformer where I'm going to go and select the total number of turns that I'm going to go and have. What we do see once again is the primary. We're going to do volts per turn. 240 volts over top of 120 turns gets me to a value of 2 volts per turn. I can take that 2 volts per turn, and now I can just go and multiply it by the total number of turns that I'm going to go and have that across. So I can go and adjust to figure out what value of turns I would need to go and have, where I would need to be tapping this thing on. They gave you the example inside of here that they're saying, look, we want to go and get out a value of 270 over here in this wiper position. Now, the way that they're doing this calculation is backwards because they're starting to talk from the main primary side. They're saying, this is what we want to have out of here. What am I going to apply? Now, it's not the way where these things are going to go and happen. What we're going to do is we are going to go and apply a value of voltage, and we will adjust the turns on the output. We don't ask Hydro for what we want. We got to adjust to what Hydro is willing to give to us. You can try asking them. It's just not going to go very well. It's hilarious. They will shoot you down hard and fast. All right. Let's go and take a look. Let's say that we do need this 270 volts, and if I've got volts per turn, 2 volts per turn, 240 volts over top of that, 120 turns on my in feed, that would mean that I would take this value, my desired voltage, 270 volts, and I would divide that by my volts per turn. Divide by 2 equals a value. So I'm dividing out the volts per turn, the volts by the volts per turn, which is just going to cancel volts, telling me that I need to have 135 turns at that point. Lovely. That's literally as simple as this is going to be. You want to try another one that's not in the book, maybe? Sure. Why not? Let's say that we are looking for a value of 120 volts out of it. Okay, we got this 240 volts in. We want to now go to a value of 120. How many turns do we need to go and move this to? Well, we're just going to go and take that value, our desired value voltage, divide it by my volts per turn set by the primary. So 120 divided by 2 tells me that I need to span 60 turns. So I'm going to take this jumper and I'm going to move this thing down right over there. That's where I would be tapping off my 120 volts over top of that 60 turns. All right, now let's talk a little bit about dangers that we are going to go and have. This one talks about a circuit inside of this figure 10 that has a high primary voltage, 12 kV. Okay, it's not super high actually in the scope of electrical things, but it's pretty dang high still. If an open circuit occurred at point X, what voltage would be impressed across the secondary terminals of the autotransformer? Well, let's first, before we start taking a look at what this thing would look like if it was bad, let's look at what this thing would look like if it was good. If it was good, what we would have is this entire winding spanning all the way across here. What we're doing is we're going to go and have many, many, many turns, and then we're going to go and tap off just a fraction of them. Really, it's going to be, what is that going to be, a thousandth of them? I guess, 100th or 1,000, I can't do the math in my head right now, but we're going to be tapping off a small amount of them to go and get ourselves this 120 volts. If we end up with this open inside of here, though, it changes from being an autotransformer to now becoming what we would refer to as a series inductor over here. That last little autotransformer section has just been, dropped right out of there. What does an inductor do? Well, it opposes a change in voltage, but the voltage still is going to go and win. So what we now have is we are going to go and have a 12 kilovolt source. We are going to go and have our load that is going to be subjected to pretty close to 12 kilovolts. So it would really depend upon the Q factor of this inductor that we would have, right? This partial transformer, it would be an inductor as soon as we lose that secondary winding. So whatever the Q factor is, that the amount of volts that I'm going to go and drop across there, we don't know what that is. Let's say that we're even dropping, 200 volts over top of it. Even if we're dropping 200 volts across it, we're still going to be at, 11.8 kV over top of our load. Our load is only rated for 120, which means that that sucker is going to go and blow. We do not use ridiculously high values of voltage. Why are they showing us this? Because later on we are going to go and cover what is referred to as instrument transformers. Ooh, that's the wrong color. Instruments. And instrument transformers are going to be used to go and measure small ratios of voltage off of larger systems. Do we have 12 kilovolt systems? Absolutely. Is Hydro still want to meter them? Yes. Do they want to build a 12 kV meter? No, that thing would be ridiculous. So instead, they use 120 volt meters, but they have to step down. And if they use an autotransformer to go and step down, there's massive, massive issues that could happen if this thing opens up inside. They want to avoid that. We're going to take a look later on at a capacitive voltage divisor, and then we can go and, sort everything out from that, but they will never use autotransformers to step down these ridiculously high values of voltage. Usually, when we are dealing with a autotransformer, it is never going to be much more than a 3-to-1 ratio, high side to low side. If this was my high side of 347 volts with a low side of 120 volts, that's about a 3-to-1 ratio. It's a little bit underneath that 3-to-1 ratio that I would have. And if I were to go and have a good operating transformer, perfect, that's going to be fine. If I were to have that open over there, at that point, I'm going to be, somewhat close to where I need to be. All right, that is those ones over there. All right, the last one that we have is just going to be a unity type of one where we're almost at the same value on our primary side as our secondary side that we are going to have. This does not necessarily have to be a ridiculously high value of voltage for this hazard to go and exist. In a lot of cases, this thing could be something like that 240 volt that we saw before to that 208 volt that we had before as well. If we have got something like this where we've got a good transformer, and I'll be honest, it's pretty rare that the transformer windings fail. Usually it's going to be your connections as an electrician where you're tying these things into lugs and threading them together on small transformers and stuff like that are going to go and fail. But if this connection were to go and fail, what we end up with is this unrestricted stinger that's just basically going to be hanging out over top of here. We are going to once again go and change this thing into a series inductor, more or less. So this load over here is no longer going to go and see 208 volt. It's going to see pretty close to 240 volt-ish. There's going to be a tiny little bit of a drop because all of my current is still going through a couple of windings. They're going to be acting as if they were a series inductor in line with that. But what they are going to do is there's going to be no counter EMF developed out of this section over here, which means that as I drive current through here, I'm going to be driving a ton of flux into that transformer core. That flux, as it drives into that transformer core, is going to flux out the rest of this over here. And we're going to run into this situation where we are going to go and have what we refer to as hysteresis effects. Basically, because we don't have any counter EMF inside of these, we are not going to get any sort of a magnetic reluctance. This thing is going to go and saturate really, really quickly. The instant that we start crossing with our sine wave into there, we're going to almost instantly drive this thing into magnetic saturation. And then it's going to go and stay in magnetic saturation all the way until we get to about here, and then it's going to drop out of magnetic saturation, just because there's no counter EMF being developed by this winding inside of here to counter that. What happens is when we get this really, really rapid drop over here, you should remember this formula here, E is equal to negative L delta I over top of delta T over here. And so what we get on this chunk over here is that every time we get this really, really rapid drop of current over top of time, this can be directly related to flux, right? Ampere turns that we have over here. What we get is we get this wicked fast drop, and then that's going to go and generate a fairly high amount of voltage. You could also do it off of EG is equal to BLV. You're going to have a really high velocity in the drop on your magnetic field as it switches over from one side to the other, which is just going to go and kick out massive amounts of voltage. So what you could see across here is you're going to go see arcs and things like that, high dangerous values of voltage that can sometimes be, tens, if not hundreds of the actual size. So if you get one of these that, your transformer is loose, is open on the inside, you got to be careful because you're going to go and get stung. Low current, but super high value voltage. It's going to be like having barbecue igniters across your fingertips. It just stings super high, and it's thankfully it's going to probably travel across the surface of your skin, but still it's going to be an electrical hazard. Be careful with them. Do make sure if you're doing these, this is not a danger, so much in and of itself the way that the previous one was. This load is probably not going to blow up, having 240 volts over top of a 208 volt one, but it's going to run a bit hot, might get a little bit funky in its operation. The danger is always going to be to the person that's coming in to find out why the load has gone funky, and that's going to be you as an electrician. All right, that is Learn Test 13.